Angles and triangles are very useful in a lot of different ways, and sometimes they're unexpectedly useful. I don't know how often it's used anymore, but historical contexts have separated decimal parts of degrees, which is a measurement of an angle, into different units, namely minutes and seconds. So, for degrees, if we had something like 12.38 degrees, what we can do is we can actually break down this 0.38 degrees into minutes and seconds. This is more of like a nautical thing they used a long time ago, and they use minutes and seconds because degrees is like an angle of a circle, and minutes and seconds are of a clock, so it's a circular. So that's the reason why it's that idea. Degrees is really just replacing hours. Think of it, you can think of it like that. Except now there's 360 degrees in a full circle rather than just 24 hours in a full circle. Anyway, to talk about degrees, minutes and seconds are only the decimal part. To find the minutes and seconds, it's quite simple. We just take, first off, the decimal part of the degree and multiply it by 60. This will give you 22.8, and this is going to be in minutes. Now to find the seconds, we take the decimal part of the minutes and multiply that by 60. And this gives you 48 seconds. Minutes and seconds are used given the apostrophe and double apostrophe. That's shorthand for minutes and seconds. I should say minutes. So 12.38 degrees is the same thing as 12 degrees, 22 minutes, and 48 seconds. I believe they used this back in the day so they didn't have to deal with decimal numbers. However, since calculators are so abundant now, there's really no reason to use minutes and seconds. This 12.38 is actually easier to work with than this 12 degrees, 22 minutes, and 48 seconds. Now, to go backwards, it's quite simple. We just take what we have. So let's look at 12 degrees, 22 minutes, and 48 seconds. 12 degrees, 22 minutes, 48 seconds. What we're going to do is we're going to add up each part with a division. So this is 12 degrees plus 22 minutes is the same thing as, well, think of it for an hour. 22 minutes of an hour is 22/60th of an hour. And it's the same thing with degrees. So this is 22/60th degrees plus 48 is, this is 48/60th of a minute. And then 48/60th over 60 of an hour. This is the same thing as just saying 3600th. So to get minutes to degrees, seconds to degrees, we take 48 and divide by 3600. This will give us 12 plus 22 over 60 is 0.366, repeating, degrees plus 48 over 3600 gives us 0.013 repeating degrees. If you add these up, you would get 0.36 repeating and 0.013 repeating. Those actually add up just like 22 over 60 and 48 over 3600. I meant to add them. We can combine these fractions by reducing them and then getting them to be common denominators. We can divide this by 2, divide 3600 by 6, I think 48 divided by 6. Yeah, 40 divided by 6 is 8. 3600 divided by 6 is 600. Divided by 2. 4 over 300. And we just multiply this one by 10 over 10. It gives us 110 over 300 plus 4 over 300, which is 114 over 300. And 114 over 300, put that in a calculator, you get just 0.38. The reason why you wouldn't want to do just this, I guess you could. I think if you rounded it, it would work out nicely. This would be 0.36. This would be 367, 0.013. If you added those together, that would give you also 0.38. What's important to note here is that the repeating and both of these cancel. And this whole thing just becomes 12.38. If you had rounded differently, you would get probably a different number for that. But we know it's supposed to be 12.38. That's what we started with. But this right here is the process. I know all this extra work was a little bit confusing because I was trying to get it simpler, but that's all you have to do here is just divide the minutes by 60 and divide the seconds by 3600, and then you can add them all up and you get the degrees in just degrees with a decimal part, which is much easier to work with than the minutes and seconds. Now, speaking of the unit of degrees, this actually, angle measurements shouldn't actually have a unit, but degrees was kind of invented to make it easier to work with. The more mathematically sound unit is called the radians, and that relates directly to the radius of a circle. The unit radians is just kind of talking about the area or the circumference of a circle. In a circle, if you were to go all the way around the outside, this measurement here, so we can kind of think of it like this measurement here, this is 2 pi radians. It's RAD, rad for short. And since a circle also has 360 degrees, then 360 degrees, just wrote that, equals 2 pi radians. It's the same unit. 360 degrees is 2 pi radians. And so what we can do is we can create a unit conversion out of this as 2 pi over 360 degrees, which of course the 2 can be reduced out of both. And so this is normally written as pi over 180, pi radians over 180 degrees, or you could write it as 180 degrees over pi radians. That's the unity fraction you can use to convert to and from radians and degrees. So if I had 1 radian, how many degrees is that? So we're going to multiply this by the radians need to go on bottom, so the units cancel. And the degrees go on top. We really just have 180 over pi degrees. Whatever that decimal number is, 180 divided by pi, or 3.14, gives us approximately equal to 57.3, I'll go 2 places, 32 degrees. So 1 radian is about 57.32 degrees. Okay, and to go from degrees to radians, well, we just take the degree measurement and put it over 1, multiply this by, now the degrees need to go on bottom, so they cancel. And we have pi radians on top. So we have 37 times pi over 1 times 180, which is just 180. And these are radians. Putting that in the calculator. Again, I'm using 3.14 for pi. 0.64, I'll go 5 radians. There's 2 pi radians in a circle, and pi is about 3.14, so 2 pi is approximately equal to 6.28. So 6.28 radians in a circle, which is a weird number to work with, but a lot of times in mathematics, we leave the pi in the number, and it makes these types of numbers a lot better to work with, because the pi is really where all the weird decimal part comes from. So our next topic is to talk about sectors. Sectors are really just portions of a circle, like I have here. This is a sector S. And specifically, they are central angles of a circle that sweep out a portion. So this is a central angle here, and it's sweeping out this portion, this S portion of the circle. And so that's a sector of a circle. A lot of times we want to know two things. What's the arc length? Or in other words, what is this blue length here? If I can draw it. Okay. And then we also want to know what is the area, the red thing of the circle, or of the sector, sorry. Now, these two formulas that we use are actually we already know them. The sector, or the arc length, we say S for the arc length. S is actually the blue line. It's actually called arc length, but that's what they just use the capital letter S. The arc length is the radius times the angle, the central angle. So the central angle here is A, and this is the radius. Of course, this is also the radius, because this right here is the center of the circle. So we take the radius times the angle, and we get the arc length. Now, it's important to note that in both of these formulas, A is in radians. You always have to have radians. That's radians is what I said before, the mathematically sound unit for angles. It is actually a unitless unit. We say rad for the unit just to designate that it's radians, but that's more of like a convenience. It's not actually a unit that's got an actual physical thing, if that makes sense. It has to be in radians. If it's not, you're going to get the answer wrong. So if you have degrees, change it to radians first. Now, if I look at the entire circle, so look at the entire circle here, and say that's A, and the radius is R, well, then A is going to be 2 pi. So the arc length, which ends up being this measurement here, equals the radius times 2 pi. That's the same thing as 2 pi r, or in other words, 2 times the radius is the diameter, pi times diameter. And you see the blue circle, the blue line here goes all the way around the circle, but that's also called the circumference. So the circumference formula here is actually the exact same thing as this arc length formula. It's just a special version. It's the entirety of the circle. How do you use the arc length formula? Well, it's quite simple. Let's say A is 30 degrees, and let's say the radius is 2 inches. What's the arc length of that sector? So just to kind of give a picture of it, 30 degrees is about that. We're looking for this thing here when we have a 2-inch radius. What's the arc length? In other words, what is this outside length here? To find that, we just got to do first change A into radians. So I'll say 30 degrees, pi radians, degrees are on bottom so they cancel. 30 and 180 can reduce to 6. Pi over 6 radians, which is approximately 0.523. Okay. And now to find the actual arc length here, we do the radius, which is 2 inches, times the angle in radians, which is 523. That gives us 1.046 inches. That's what that blue measurement would be for these conditions. Okay, now to find the area of this sector, we use the same formula. Well, let me write down the formula first. Area of the sector equals 1/2 AR squared. And then if we look at the area of a full circle of the full circle, so the A would be 2 pi, then the area of the sector becomes 1/2 2 pi times r squared. The 1/2 and the 2 cancel, and we get pi r squared. This is the area of a circle. So it's actually, again, the same formula we've already used. It's just a little bit different in its form. Now, to find the area of this sector that I drew here, all we have to do is plug in the angle that we found, which was pi over 6 radians, or 0.523 radians. And so the area of our sector be 1/2 the angle, which was 0.523 radians, times the radius, which was 2 inches. That's going to be squared. Okay, 2 squared is 4, and then 1/2 times 4 is 2. Well, I'll just write like this. Two squared is 4. And then you can just go one left to right, multiplying it out. And doing that, we get, interestingly enough, also 0.146. But it's not going to be the same unit as this. We have an area here, so the area is going to be inches squared because we're in inches. But just how the numbers worked out, because of this 1/2 and this 2 squared, they end up being the same number, but they aren't the same thing because one's inches and the other one is inches squared. Okay, the last topic before we do some application problems is special triangles. And there's 3 special kinds of triangles. One that's kind of a little bit different, but two main special triangles, namely the 45-45-90 and the 30-60-90. The 45-45-90 is an isosceles right triangle. Both of the angles must be 45 degrees because if one angle is 90, the other two, since it's isosceles, have to equal the same thing. And they have to add up to 90, so it has to be 45 and 45. This is a special triangle because it's got a nice nice shape, and it has nice properties, namely it's isosceles. And if the sides are like x, since they're both the same, they're both going to be x, then the third side is going to be square root of 2 times x. So you actually don't need to know all the different sides to use Pythagorean theorem. Because it's a special triangle, we already know, using formulas and things, to find out what's the third side. So for instance, if I had a triangle with side length 2, like 2 feet, for instance, then I can find the other 2 sides very easily by just saying, I know this side is going to be 2 as well, because it's isosceles, and isosceles has 2 sides that are the same length. And the third side, the hypotenuse, is going to be 2 root 2. And I don't have to use Pythagorean theorem to find that. I already know it because of the special triangle that 45-45-90s are. 2 times root 2 is approximately 2.83. Okay, 30-60-90 is very similar. The smallest angle is going to be 30. The next is going to be 60, and then 90 is the right triangle, or the right angle. And this one also has a special properties. Namely, if this side is x, then the side opposite the 60, so the side opposite the 30 is x. The side opposite the 60 is root 3 times x. And the one opposite the 90 degree angle is 2 times x. So once again, if I had the small side being 2 and this was a 30, 60, 90, then I know this side's going to be root 3 times 2, and the third side is going to be 2 times 2, or 4. Root 3 times 2 is approximately 3.46. So once again, I do not have to use Pythagorean theorem to find the different sides. I can just use the property of 30, 60, 90 triangles. Now the last triangle is more of like an application triangle. You can use this for, I don't know, making walls of a house, just trying to square up any kind of side to where you want to have a 90-degree angle. This is the triangle that you can use. It's called a 3-4-5. And this is how it works. If you have a cord, like a piece of rope, that's 3 feet long, for instance, and you have on each side of this cord, you have one rope that's let's say 4 feet long, and on the other side it's going to be 5 feet long. Obviously, I'm not drawing this to scale. I should try and draw it better, but I'm not really sure how. If you line up these two ends, so you move this in so that it's touching that end, what you're going to end up getting is a triangle that has a right angle. The other angles are going to be some weird measurements, so that's not necessarily the nicest thing. But what it does do is it creates a right angle necessarily, because this one's 3 feet, this one's 4 feet, and Pythagorean theorem says 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and we know that the Pythagorean theorem says this side squared, namely 5 squared, that's going to be the hypotenuse. So 3, 4, 5 is what's called a Pythagorean triple. Namely, it's 3, 4, 5. Those are 3 numbers that work with the Pythagorean theorem. Another Pythagorean triple that'll also work with this is 5, 12, and 13. Of course, 3, 4, 5 is much easier because they're smaller numbers. But 5, 12, and 13 also have this property that 5 squared plus 12 squared equals 13 squared. These are called Pythagorean triples. Pythagorean triples. All right, let's look at some application problems with some of the stuff that we use in this section. What is the area of a flower bed that is shaped as a sector with radius 60 feet and central angles 40 degrees? And then there's another question there. So let's first draw this thing out. So here I have a circle, and I'm going to make a central point. And it says it's got a central angle of 40 degrees. So let me draw it like this. It's going to be about that. This is 40 degrees. And it's got a radius of 60 feet. So just ignore the rest of the circle. This sector here, that's what the flower bed looks like. It's just this little piece of pie. And that is a 40-degree angle, and this both this length here, you write that, is 60 feet, and this length is also 60 feet, because those are the radius of the circle. Okay, it's asking for what is the area of this flower bed. Well, this is just a sector, and so we use the sector formula. Sector area, I should say area of the sector. This equals 1/2 the angle times the radius squared. Well, we can't use the angle because the angle is 40 degrees. We need to first change this to radians. I'm going to multiply this by 180 degrees over pi radians. The 40 and 180 can reduce the 20 and 90, and then 10 and 45. This is still just going to end up giving us 10 pi over 1 times 45 is 45 radians, which is approximately equal to 0.698 radians. And now we can use that angle in our formula. 0.698 radians times the radius squared. Putting this in the calculator gives us 698 times 60 squared, 1256.4. This is going to be in feet squared since the radius was in feet. So that's the area of the flower bed. Quite a big flower bed. Now, if the flower bed has shrubs every 2 feet around the outside curve, how many shrubs are needed? So every 2 feet around the outside curve. We're trying to figure out how many shrubs, which are these red dots here, do we actually need. I don't know, my drawing there is probably inaccurate, but we're just trying to say that every one is 2 feet around. We can do this quite easily by knowing what is this distance here, and then dividing that distance by 2, because it's every 2 feet. So it's asking how many times does 2 feet go into that distance. That's all we're trying to do. Well, this distance here, this blue distance, is the arc length, which is S equals R times A. The radius is 60. The central angle in radians is 0.698. Multiplying that out gives us 41.88 feet. That's the distance of the blue line. Now we just need to figure out how many 2 feet segments fit in 41.88 feet. And we just take 41.88 divided by 2. That gives us 20.94. But of course, we can't put 0.94 of a distance for a second or for an additional bush. So we would only say 20. Right? It's asking for how many shrubs are needed. So 20 shrubs are needed to fit in this 41.88 arc length. So a carpenter is building a corner cupboard shelf, and it's got the shape of a 3/4. The shape is 3/4 of a circle. So this is kind of weird because I would imagine a corner cupboard is like this, but what they're saying is that the shelf looks like this. I can draw an accurate circle. That's what the shelf looks like. The radius is going to be 11 3/4 of an inch. And it's asking how many square inches of shelf will the cupboard contain. So what's the area, right? Well, we can use the area of a sector, which is 1/2 A times R squared. We need to know what is the angle and what's the radius. We know what the radius is. I want to write the radius not as a mixed number, but as a decimal. 3/4 is the same thing as 0.75, so this is going to be 11.75 inches. Now the angle is this angle here. We don't want this angle because that's the angle that we're not trying to find. We're trying to find the big angle. That's the actual angle of the sector. And it's 3/4 of a circle. Well, if a circle has 360 degrees, then 3/4 of this is just 3/4 times 360, which is 270 degrees. So that's the angle here. Now, of course, we don't want the angle in degrees. We want it in radians. So we're going to go 270 times pi radians over 180 degrees multiplying that out, we'll get 4 divided by 180. That gives us 4.71 radians. And so the area then is 1/2 radians and 11.75 inches squared. So multiplying this all out, times 11.75 squared gives us 325 point, I'll go to 2 decimal places. Since it doesn't say anything, I'll just do 2 decimal places. This is going to be in inches squared since our unit is in inches. So this shelf has 325.14 inches squared area for things to be set up on it.